In the last 4 lectures, we had been looking at the simultaneous equations model. We have looked at the different aspects of the simultaneous equation models. Primarily, we have discussed the identification problem. The identification problem is fundamental to simultaneous equation models, because unless an equation is identified, we cannot estimate its parameters. So, before estimating the parameters, we need to check whether the equation is identified or not. Now, in this lecture and in the subsequent lectures, we will assume that an equation is identified or the system as a whole is identified, and then what we will look at is how do you estimate the parameters of this identified equation or this identified system. Let us go back and look at the simultaneous equation models. We have b y plus gamma x is equal to u, where y are the endogenous variables. There are capital G of this endogenous variables, and x are the exogenous variables, where we have capital K exogenous variables. B and gamma are the coefficient matrices, and u is the error or disturbance term. We assume that expectation of u is 0 and the dispersion of u is sigma. Now, suppose we have n observations y I x I from this system. So, in this case, remember that y I x I would be a vector of dimension g plus k, because there would be g endogenous variables for each observation and k endogenous exogenous variables for each of them. So, taking the endogenous and exogenous variable for each of the observations, we have g plus k elements for each observation. Now, if you write this model, then we have taking all this n observations together, we can write it as B and then a matrix of y1, y2, yn, where these are column vectors, plus gamma x1, x2, xn again are column vectors, and similarly u. Or we can write it in matrix notation as by plus gamma x is equal to u. This we will call equation 1. Assuming that these n observations are independent, expectation of u of course is always going to be 0, but the dispersion assuming independence would be in Kronecker product sigma. Now, this would be the basic setup. Now, estimation, remember, needs to be carried out only for the identified equations. So, if an equation is not identified, we do not carry out its estimation. Now, there are broadly 2 methods of estimation. The first one is the single equation methods, and the second one is the system methods. In the single equation method, each identified equation is considered in isolation and its parameter estimated. So, we look at each of these identified equations one at a time and then estimate its parameters with regard to its own, with regard to that just cut this. Just in the single equation system, I am starting from this. Okay. In the single equation system, each identified equation is considered in isolation and its parameters estimated. Of course, what happens here is we fail to take account of the correlation among the errors, because we are taking them separately. So, the correlation does not come into the picture at all. Whereas, in system methods, we take all the equations simultaneously and estimate the parameters. In this case, of course, we can take cognizance of the correlation between the different errors, but remember, in this case all the equations need to be identified, because the system needs to be identified before we can carry out its estimation. So, in the single equation methods we would use, if all the equations are not identified, we will be looking at only the identified equation, but then we will not be taking into account the correlation between the errors. In the second one, we need the equations are all identified, and we can in that case take account of the correlations between the equations. We will start with the single equation estimation method. In this case, we will look at equations one by one. So, we will consider in general the jth equation, and we will assume that the jth equation is normed. So, suppose there are gj endogenous variables including the response and kj exogenous variables in the jth equation. Mind you, all the variables will not be there in each of the equations. So, g minus gj endogenous variables are missing and k minus k exogenous variables are missing from the jth equation. We need this for identification, remember. So, we can write the model as yj is equal to yj beta j star plus xj gamma j star plus uj. Now, remember that we have normed the jth equation. So, the coefficient of yj should have been beta jj, but we have taken that to be equal to 1. This is the equation that we will be concerned with, and we will be estimating the parameters beta j star and gamma j star. We will call this equation equation 2. Now, let us give a description of the variables and parameters involved. What is yj? The small yj is the n-dimensional response vector. This is the jth endogenous variable. In this case, is the response vector. What is capital Yj? This is the n by gj minus 1 matrix of endogenous variables. Mind you, there were gj endogenous variables, but one of these endogenous variables is the response yj. So, leaving aside the response, we now have gj minus 1 other endogenous variables in the equation, which we will call capital Yj. Xj is the n by kj matrix of exogenous variables. So, we had kj exogenous variables, and this constitute the matrix Xj. Beta j star is the gj minus 1 vector of endogenous coefficients, and gamma j star is the kj dimensional vector of exogenous coefficients. Uj, of course, is the vector of disturbances. Now, remember that Yjm and Xjm, these are n by gj matrix of endogenous variables and n by capital K minus kj matrix of exogenous variables, which we have left out from the jth equation. So, we denote them by Yjm and Xjm, m standing for missing variables. So, these are the variables which are not there. So, if you look at the original y of capital G endogenous variables, we can partition this into 3 components. One is the jth response variable, in this case the jth endogenous variable yj, small yj. The other is the capital Yj, which are the endogenous variables in the jth equation besides the response, and Yjm are the g minus gj endogenous variables which are not in the jth equation. Similarly, we can split x into 2 components, xj and xjm. Xj is those variables which are there in the jth equation, the exogenous variables, and xjm are the exogenous variables which are not in the jth equation. So, also we assume that the included variables are arranged before the excluded variables in the equation. So, the yj comes before yjm, xj comes before xjm, we can always rearrange the variables. Then the jth row of A, which is B and gamma, these are the structural parameters, would be alpha j, which is 1 because the first variable yj has a coefficient of 1, that is a response variable. Then you have beta j star prime with a minus sign, because if you remember how we wrote it before, this time we are taking all the variables on the right hand side except the response, and therefore, the sign becomes negative. Then you have the 0 for the left out endogenous variables. Then you have the exogenous variables which are in there, and finally the exogenous variables which are left out as a 0 coefficient again. So, the structure of alpha j, the jth row of the A matrix would be this. We will now do the indirect least squares. Now, what is the indirect least square method? First of all, let us go back to the model. Model was by plus gamma x is equal to u. We could not estimate b and gamma directly from this, because the response and the endogenous variables which are not the response but are there in the equation, these are going to be correlated with the error. So, we cannot have correlated explanatory variables, and hence we cannot directly do the least squares on the structural model. Instead, we go for the reduced form expression, where we take, since B is a non-singular matrix, we can invert it. So, we take y is equal to minus B inverse gamma x plus B inverse u, and we wrote it as pi x plus v. So, we can express the endogenous variables solely in terms of the exogenous variables, and since we can do that, we can apply the ordinary least squares on this equation which we call equation 3, and get pi hat as y x prime x x prime inverse. So, we get an estimate of the reduced form parameter. Now, since we have the relation b pi plus gamma I k is equal to 0, or as we saw before, we wrote b and gamma as a and pi and I k as w. So, we have a w equal to 0. Now, since this happens, if I look at the jth row of a w, so jth row of a is alpha j prime. So, the result must hold for alpha j prime as well, and hence we have alpha j prime w equal to 0. But remember that alpha j prime is 1 minus beta j star 0 minus gamma j star 0. This is a vector, and you have pi and I k equal to 0. So, we have this equation where we substitute alpha by the actual parameters now. So, what we get is, if I substitute pi by pi hat now, and then we do a little bit of algebra, what we come to is, take the x part on the right hand side, we have 1 minus beta j star 0 y x into x prime x x prime inverse is equal to gamma j star 0. Now, the minus gamma j star, because we are taking it to the right hand side, itself becomes, now it becomes plus. And then a little bit more simplification, x x prime inverse can be taken to the right hand side, and now we have a equation here. So, we have 1 minus beta j star 0 y x prime on the left hand side, gamma j star 0 x x prime on the right hand side. Now, remember that y is composed of 3 components, y, yj, yjm, and x of xj and xjm. So, on taking transpose, if we bring x first, then we can write this as x into yj minus x yj beta j star yj m 0, and similarly for the right hand side. So, ultimately, after a little simplification, we come to the last equation here, where we have a matrix x yj, first component, and the second component is x xj, and we have 2 components for the vector of parameters beta j m and gamma j m, which is equal to x y j. These are the normal equations which we need to solve. Now, if we look at this x j star and x j m prime, y j, x j, etc., we have a equation system here. And how does the equation system look like? If you look at 1 and 2, then this equation system would be, 1 has, remember, kj equations, and 2 has k minus kj equations, if you look at the orders. The number of unknown parameters is gj plus kj minus 1. So, given this, what we have is k equations in gj plus kj minus 1 unknowns. So, we can solve these equations and get the estimates of the parameter beta j star and gamma j star. But then for a unique solution, it would be required that kj, that is the number of first set equations in 1, and k minus kj is the number of equations in 2. This 2 would be the total number of equations, should equal to the number of unknowns. Now, if I add g on both sides, remember kj cancels out from the both sides in the previous equation, and if I add g now, so we have g plus kj minus kj and g plus small gj minus 1, and a little simplification then shows us that g minus gj plus k minus kj would be equal to g minus 1. What is g minus gj? This is the number of endogenous variables left out. And what is k minus kj? It is the number of exogenous variables that are left out. And by the exclusion restriction, so we have R restrictions where R should be equal to g minus gj plus k minus kj, that is the number of variables which have been left out. So, R must be equal to, so the right hand side is g minus 1, left hand side simplifies to R, and therefore, R must be equal to g minus 1. And what does R equal to g minus 1 imply? It implies that the equation must be exactly identified. So, in the indirect least square method, this can be applied only when the equation is exactly identified. Of course, it needs to be identified, but it should not be over identified. If over identified, so there is an equation with over identified which is over identified, then we cannot use the indirect least squares. So, it is slightly restricted in the sense that it only can be done when you have exactly identified equations, and we will see that again from a different view in the next lecture. In conclusion, we have today looked at the different types of estimation methods for simultaneous equation. Broadly speaking, there are two types of estimation method. One is the single equation estimation methods, where we look at each equation separately and estimate its parameters. As opposed to this, we can look at the system as a whole and estimate the parameters of all the equations together. Both these have several ways of estimating the parameters. We started with a particular method of the single equation system, which is referred to as the indirect least squares, and saw how we can estimate the parameters of a single equation using the indirect least squares method. In subsequent lectures, we will look at a few other single equation methods, primarily the two-stage least squares and the LVR estimator.